All right, so today we're talking about a somewhat recent and somewhat not recent paper that's building on the last video. This is actually a video that I've been wanting to make for a very, very substantial amount of time. I think I've had these tabs open since like the paper was first written, and that's got to be like 2 years ago now at this point. But there was a long journey to publication. But now that we've gotten the whole process complete and publication is all done, now I can finally make the video and close these tabs. So yeah, originally the video was probably going to be like 4 videos going way more in depth and in detail in all of these different areas, such as like a video on Hamiltonian Monte Carlo, a video on the Heisenberg picture of quantum mechanics, and then a video on QDHMC, and then a video on the implementation. But we're just gonna speed run it in one video. If there's huge interest or something, I can go into more detail on each of the sections and of what I described or something else. But I don't think that'll be super necessary. As usual, I guess there's some assumption of background knowledge in terms of sampling and in terms of quantum computing. I will say that watching the previous video is a good introduction, and I'll do some speed covering of Hamiltonian Monte Carlo, but I'll also link a number of introductory materials in the description, so you can definitely check those out as well if you are interested in learning more about Hamiltonian Monte Carlo. So in general, let's first go to the PDF. So in an exact same vein as last week, we're looking at using quantum computers to accelerate sampling routines. So what are we doing this time? Well, if you remember our last video, right, where we had this quantum enhanced MCMC, the idea was basically for this discrete sort of Ising model setup, trotterized Ising model, simulate it, and then use that as proposals to your function. And now the idea is very similar. In fact, in the introduction, we basically say, we're directly building on this. What we do is we basically say, combine this idea of using quantum computers to enhance the proposal functions of sampling algorithms, and combine it with this specific approach to quantum simulation, this continuous variable QAOA, and what that yields is actually a direct sort of quantum analog almost of Hamiltonian Monte Carlo. So the first thing we're going to do before we get into anything in detail of the paper algorithm is we're going to talk about Hamiltonian Monte Carlo. So we talked about sampling, right? We want to draw samples from P of X, but we only have access to this unnormalized log likelihood that physicists will often call an energy function. And so how do we do that, right? Well, we saw in the discrete case, you can do all sorts of methods that we talked about last time. In the continuous case, also all sorts of methods, right? There's these Langevin-based samplers. There's all sorts of Gaussian samplers. There's much more crazy things. There's variants of all of these. For example, probably the most popular is something called NUTS, which is a no U-turn Hamiltonian Monte Carlo. And so there's a lot of things you can do, but one of the most common and foundational methods is called Hamiltonian Monte Carlo. And so what is that? And we're actually gonna ignore this section of the paper for now. Let me zoom in, but we're gonna ignore it because we're gonna go to a blog post that I think explains it very well. And so this is one of the blog posts that I will be linking in the description. And so what we have, going over here is, so yeah, credit to Alex for this blog post, which is very helpful, and I will just refer everyone to this for Hamiltonian Monte Carlo. And the idea is basically, well, we've covered Monte Carlo and why it's needed. And we also briefly talked about temperature last time, but this is a good reminder of temperature. Right, in our equation up here, we have this p of x equals 1 over z, which is the partition, and we have e over t as the exponential. So what that means, you often see it's just written as beta times t, where beta is 1 over kt, sort of the Boltzmann constant there. And so in cases like this, you can see that as you decrease the energy, right, this, or the temperature, this gets smaller, which means this overall becomes a larger number that you're exponentiating. So smaller temperatures results in bigger, sharper distribution. So for example, this is very helpful. This is why I like this blog post, is just because of these figures. It is right, I decrease the temperature, it sharpens the distribution. Obviously there's some cutoff here that I can maybe do. This is a good one, right? And then if you increase the temperature, it flattens the distribution out. Obviously at some sort of infinite temperature, it's just become some sort of uniform distribution. And so this is the influence of temperature, and this will come up later in the QDHMC paper. And so the important idea here is that instead of just proposing some sort of random Gaussian walk, or even some sort of fancier method that we're not gonna necessarily discuss, the idea is basically, let's simulate the Hamiltonian dynamics of a system and use that as a proposal function. Specifically, we're going to take they say a hockey puck, I would say a marble, and you're going to flick it in a random direction, and it's going to slide along with zero friction for a certain amount of time, and then you're going to look at where it ended up, and then that's going to tell you basically an estimate of this proposal. And so the reason, right, intuitively, this sort of makes sense if you imagine, I think this Gaussian one is very clear, right? Like, if we're simulating this and we give it some random momentum, then we're able to explore a lot of areas, right? Because we could randomly kick with a very high momentum in this direction, so it's going to go up to like the sides. But in general, the trajectory is like it just slides down. That's just the way gravity sort of, if you think of this as a bowl that you're sliding your marble in, gravity is just going to pull it down on average. And so that's a decent intuition. In practice, what we actually do is we have, and this is where I'll go back to the paper, is we have a joint distribution now, but instead of just a position, we have a auxiliary variable called momentum that we're going to be simulating. And so basically we just have this Hamiltonian now, and that's just from Hamiltonian dynamics, where you have these position and momentum. And we basically say, okay, we now simulate the Hamiltonian dynamics. So these are just classic sort of physics things, where we say, okay, we simulate the change in, we're simulating, right, like the time. If we kick the marble in a random direction, we simulate the time that the trajectory that this marble goes on, which is just implicitly a function of time. And so our Hamiltonian itself is not time dependent. And so we can say, right, our change in position is the derivative with respect of the Hamiltonian with respect to momentum. So basically, right, our change in position is influenced by the momentum, and the change in momentum is this is the full this is the full distribution pi here. So pi is the probability distribution, not the unnormalized. So the log of this is just this energy function. And so this is pretty clear, right? Like the change in the change in this momentum is just going to be this derivative with respect to x of the energy. And so this is nothing new. This is literally just the canonical sort of Hamiltonian equations. And there's many ways you can simulate these dynamics, but the probably the most common method is just to do this leapfrog integration, where you can see, we're leaping over it, and all you do basically is you take a half step in the momentum, then you update the position, then you take another half step in the momentum. And for these joint distributions where you have this relationship between position and momentum, where they're sort of mutually dependent on each other, this can work quite well. And so what we have here, right, is an epsilon. That's a step size that just determines sort of the error in our integration, right? We want to simulate this, but if we make epsilon too small, then we take tiny steps, but we take more accurate steps. Whereas if we make steps very large, then we can get away with less computational work, but we have to do more error, we have more error that comes with it. M here is just a mass matrix, right? So this is, obviously, we're trying to sort of simulate real systems, and in Hamiltonian dynamics, right, we have this mass that, right, momentum traditionally, right, is mass times velocity, or mass times the derivative of position. And so here we have this inverse mass matrix. In practice, this can often just be set to some multiple of the identity matrix, or it can be tuned and optimized as a hyperparameter using a variety of methods. And then we have sort of the traditional Metropolis Hastings acceptance function here, where we sort of have, right, the difference in energy between the first state and the original state. And you'll notice potentially that there's no Hastings correction, right? This q of y given x over q of x given y. And the reason for that is because, although it doesn't look like it, the proposal function is symmetric, because what you actually do at the end is you say, okay, I do this whole process, then I set the momentum to be negative, and then if I were to reverse this, then you can actually see that this would work out. The problem, right, is that normally if you kick it this way and then it goes up the hill and then it goes down, like, it's not just going to spontaneously like go up a hill, but with this momentum reversal, which I think briefly, I guess it got cut from the paper, but there is this idea that if you need to actually prove the reversibility, then you just add this momentum flip at the end. This is not actually done in practice because the momentum is randomly resampled at the start of each iteration, so this would have no influence, right? You would just do a meaningless operation here. And you might also be saying, why is there even this differential, right? Hamiltonian dynamics are energy conserving, and so this is zero, right? This is a difference between these Hamiltonians, which should be zero. And the reason, of course, is that we're not actually simulating them, we're approximating them, and our approximation is inaccurate, and that's necessarily true. And so what this does is basically correct for inaccuracies in the simulation, and that allows us to reject steps that are sort of inaccurate integrations. And so, yeah, ideally, with perfect integration, our acceptance probability would be 1. And so that's the basic idea of Hamiltonian Monte Carlo. You simulate these Hamiltonian dynamics to get better proposals. Now, this comes at a cost, right? The cost is twofold. One is that you do multiple steps of this for every single proposal. So this is a potentially costly thing, right? Not additionally, we need to be able to differentiate our energy function, which is not universally true, but we repeatedly call the gradient of this function, which, maybe we have in closed form, maybe we have to autodiff through this function, and then we repeatedly do this integration process in a single step, and then we have to do lots of steps. So this obviously comes at a cost of computation that we need to make sure is justified. And so the advantage, though, is that this often yields substantially better proposals than some sort of random walk, especially in continuous, right? This is obviously a continuous function that we're evaluating here in the continuous function regime, this is often much better than random walks, just because random walks, right, you're literally covering an infinite space with a random walk. That's just intuitively not an ideal system. And so now the idea is, okay, I just walked you through Hamiltonian Monte Carlo. Let's talk about quantum dynamical Hamiltonian Monte Carlo. And I don't want to overcomplicate things, because really the idea is this. You take this paper where we say all we're going to do is propose a function and then feed that proposal into the metropolis accept reject stage. And instead of doing an Ising model, we're going to do this model, this CV QAOA model. And what happens, and what we show is what happens if you plug these two together, basically you pop out a HMC algorithm. And so specifically, this is operating on continuous variables. So that's one of the biggest differences between obviously this discrete Ising model and this continuous version, is that it is continuous. And so there's two important components. First is that it's very doable on continuous variable quantum computers, but not every quantum computer is a continuous variable quantum computer. There's different modalities, right? Not everyone has Q modes. Some people have qubits or qdits. And so how do we do this, especially for our simulation algorithms? How do we do this on digital quantum computers? And it's really not that simple, or sorry, it's really not that complicated. It's somewhat simple. And all we're doing here is basically taking this paper. You can see we're just building very directly on a lot of work. We take this paper, which proposes some tooling to do continuous variable operations, such as continuous variable quantum harmonic oscillators on digital quantum computers, and we just take that idea and we just do it. And it's really, nothing too complicated. So what do we do? Let's first summarize the algorithm. First, we prepare a bit string X, and this bit string is either, I guess, a continuous variable quantum sort of setup, in which case it's not a bit string, I guess, but it's a continuous variable. I don't know what they call. I actually don't know what a bit string would be. A Q mode string, I don't know. And then we represent f of x in continuous variable operations, and we'll talk about this more in the implementation section. And then we define our Hamiltonian, which just is this momentum and position Hamiltonian, right? This is just sort of the canonical Hamiltonian, where you just have this 1/2 p squared plus your potential. And then you do random trauterization, and you measure a bit string or your Q mode string, and then you do the standard accept reject. And so what we have basically is, how do we do this on digital quantum computers? We're not really going to talk about this much right here. It's because it's not really that important in some sense. I mean, however you want to do this on a digital quantum computer, you could invent any algorithm you have in your mind, and if it works, then it works. Like, this is not incredibly important to the algorithm itself. This is just sort of as an example, a way you can do this on digital quantum computers, but you could do it in any other way, or you could do it in analog systems. It doesn't really matter. But the basic idea is just that basically you have a similar to, I guess, digital logic. For a given number of qubits, you just encode one continuous variable in many qubits, and that's the idea. That's it. Just like in digital machines, you have one floating point value that you encode potentially in 32 bits of information or something like that. And so it's a very similar idea. It's just a way of doing that in quantum. And in fact, if you're very interested in that, you can check out this library that we built to support, because all of our simulations were done on a digital simulator called Continuous Variable TensorFlow Quantum. And you can see you can see how it's done here. And so we'll briefly go through this specifically. Just make sure I have a few branches, both here and in the QDHMC repo. I'll link to my specific branch, but it's the one that's been updated. So basically the idea is simple. We have position and momentum operators that we actually represent, right, as Pauli strings. And so, right, you can see here what we're doing is very similar to this, to this operation right here. If you look at sort of this section right here, and you see what we're doing in here is we're just saying take this operator and apply it to a list of qubits, right? So this is basically how are we encoding one continuous position into many qubits, and this is just how we do it. And you can add and combine operations, and then utilities is not super interesting. It's just utilities, right? You can plot the wave function, you can prepare a certain integer state. What is interesting, at least to me, is down here, is the amount of work that it took to get some of these things to work in TensorFlow. Because we built everything on top of TensorFlow probability, and we wanted to sort of be fully interoperable with that. Whether or not that mattered, I don't know, but we can't just do this sort of for loops Python, control that we would do in NumPy, because we have to actually, get it to work in TensorFlow. So it has to rely on all of these TensorFlow operations. So you can see this isn't too complicated here. But what was annoying was this function right here. I remember spending a lot of time getting this annoying thing to work, right? Which basically, it's a simple objective, right? We just convert this floating point representation to some discretization. And so, but what was annoying, right, is just that you have this, you have to do these weird, scatter and add functions to do a TF while loop, and then you had to declare like invariant shapes. And so this was just, very, and then all of this, I think I adapted this or maybe copied this from a Stack Overflow. I don't see it linked, so maybe I adapted it, but all of this is just to convert floating point to binary, or sorry, to convert an integer to binary. And so you could see like it's just so much work to get it into the TensorFlow format. That was, that was a fun time writing this function. That's just like the most specific weird TensorFlow math. And maybe, if you see a trivial way to do what I did, then feel free to change it. But that's not super interesting fundamentally to the algorithm. In the subroutines, we have the core of the repository, which is computational layers that use our basic operations, right? We have a Fourier transform. We have this centered Fourier transform, which is basically how you define QFT on this style of convention position operator. You can kick a position right from one. That's the basic ideas, right? We have these discrete states that are sort of representing the sort of how fine-grained we have our continuous variable discretized at. And so we can move basically our representation to different versions or to different discretizations by kicking it from different state to state. We can kick the momentum as well, and then we can construct adders or subtractors. We can swap information. We can generate hybrid discrete continuous things. So there's lots of cool things that you can do. You can even do rectified linear units if you're very interested. And all of this too, we have some nice tests in here that you're welcome to check out. But most interesting are the examples. So we can see for the CVQAOA, all built in TensorFlow Quantum, that right, this is our discretization here, and what we have is a actual continuous problem, right? We have this quadratic problem, which is continuous, but we're able to do QAOA in this continuous variable regime. And so that's a sort of a different mentality, but you can see what this cost function looks like in the discretized version of the continuous regime. So then if we generate our QAOA model and we optimize it, then what we can see, of course, is that this 1100, which is the lowest value state, or the lowest energy, or the lowest cost state, is the most probable. We can also do interesting things such as variational quantum eigensolvers for quantum harmonic oscillators, right? So the quantum harmonic oscillator is just our usual momentum squared term, and then we have this mass omega squared, where that's just the frequency of oscillation, and x squared ensures that we have this Gaussian potential. Of course, this is known to be solved. We can write it out here. It's a whole, that's something you do all the time in an intro to quantum mechanics class. And maybe I have a video on that actually. I did briefly, like 3 or 4 videos on intro to quantum mechanics, and I remembered a single particle box and I think a Gaussian particle. I don't remember if I did a harmonic oscillator. And so all we have to do, right, is we basically say we alternate some sort of hardware efficient ansatz, which is just, layers of nearest neighbors connected CNOTs, and then single rotations, and CVQAOA layers, where our mixer Hamiltonian is just this 1/2 momentum squared, and C is our actual cost. And so what is our actual Hamiltonian here that we're working with? And you can see somewhere down here, right, is the problem definition, right, where we have this, we have this position squared, and then we have our momentum squared, and then we have this normalization. And this is not, you might say, hey, wait, you dropped a bunch of stuff over here, and you're right, I did. I just did the physicist thing of like everything equals 1 that I don't want to deal with. And so, yes, that is true. And so then when we optimize it, you can see if you squint really closely, it looks like a Gaussian. But what we can do, right, that's a Gaussian fit, is you'll notice it looks super noisy, but that's because this is with a finite number of states, and we have a very rough, right? It's very difficult to get it to be perfectly represented as Gaussian. So what we can do though is we can trace out we can trace out a few of the qubits, right? So we can basically say those are superfluous, and if we also trace out for the Gaussian fit, then we can see basically a very well fitting Gaussian. And so we don't trace out the Gaussian fit, we refit the Gaussian to this, and we see it's a very compelling demonstration of a Gaussian BQE. And so that's the basic idea of CVTFQ. I realize that was probably a tangent, but for those of you interested, it's a cool repo. So now, getting back to the paper, what we have in the algorithm itself is basically a quantum version of this Hamiltonian Monte Carlo. And so let's get into how that's true. First, let's look at the kinetic term, which is just this 1/2 p squared. And so what we can see actually is that if we basically apply this operator and we look at how x is affected by it, basically we can see that this results in a kick with respect to the momentum. And then if we do the same thing, we say, okay, how does our position affect the momentum operator through this evolution? We can see that this momentum is pushed by the derivative of this function. And so I guess this is probably unclear notation, right? Just gradient. This is gradient with respect to x. And so what we have, and so we can see actually looking from this that you can combine the position operator or the operations that happen to the position x. And if you look at the leapfrog integrator and you just ignore the sort of second half of the momentum update, you see an update that basically turns into equation 7. And from equation 7, we can see that if we just put in the quantum update, which is here in equation 5, we can actually tweak the parameters eta and lambda to be epsilon over mass and epsilon over 2 respectively, and recover the traditional symplectic leapfrog integration. And so that's essentially the idea. Now you might be wondering, how does this actually come about? And I also was wondering that. And so in the appendix, you can see I wrote out a pretty elementary, I guess, derivation of it, in the sense that we go through very many algebraic steps just from the sort of usual quantum mechanics papers. And so basically all we have to do is look in this Heisenberg picture, which is just like in the usual Schrodinger picture in quantum mechanics, right, that we usually talk about. It has a time-dependent wave function. And so the wave function, changes with time. And the Heisenberg picture sort of inverts that. It describes observables which have operators that are time dependent. So what happens then is that this is the exact same representational power. This is not like a different set of physical constraints. This is not at all a different set of physical requirements. This is just a different picture for representing the exact same physical theory. It just has its benefits in certain situations, but everything you can do in one picture, you can do in the other. And so when we look at the Heisenberg picture, basically we can describe it in relation to Schrodinger as this time. These observables are functions of time. Basically, we take the Schrodinger observable and we just smush it between the applied or exponentiated Hamiltonian. And so if we want to actually look at how our trauterization, right, which is simulating the time evolution, how the time evolution of our system takes place, we can look at this picture. And we can see specifically what makes it easy is we can directly write this derivative with respect to time as a function of this commutator. And what we do basically is we take our Hamiltonian, right? This should probably have a hat, I guess. And we say, okay, let's do this. So let's look at the time evolution of our x operator. And so all we have to do is do a pretty standard commutation expansion. You do this all the time in sort of intro to quantum mechanics classes, right? Where you just you show, for example, like how position and momentum commute and that they don't. They have this, right? Things commute if this is equal to 0. And there's lots of things that you do. And so if you just go through the whole math that we won't go through right now, you basically see that the derivative, the change basically that this affects, this smushing of the position basically results in a momentum kick. And we can do the same thing for looking at the evolution of momentum through time. And here we see, right, that momentum, right, is like I h bar d dx, or I over h bar, I don't remember. And so that's where the gradient comes from. And we can simplify this all out and we see that we get out this negative gradient kick. And so that's just exactly what we have here, right? So now that we've sort of popped out, if you will, the leapfrog integration method from the quantum realm, we can do some more, bookkeeping, if you will, and just say, look, this meets all the usual requirements of these HMC, MCMC algorithms. You can show a bunch of things pretty trivially about like volume preservation and things like that. And one of the other things is detailed balance condition, right, which is something else that we talked about briefly from any other point, right? You have to be able to get back in some sense, I guess is sort of an intuition to have. And in HMC, right, you have this sign flip at the end for the momentum to ensure that it's reversible, that you have a non-zero probability of ever, reverting. And fundamentally, that doesn't matter, right, in computation, because you randomly sampled the momentum. And so the kick is irrelevant. I guess this is the intuition I wrote. The Hamiltonian dynamics, right, only go forward in the sense that if I was just evolving like these dynamics in like time, then you can't go back in time. And so, right, we would sort of never accept proposals. And so adding a sign flip on this momentum just ensures the reversibility. And what we show is also that if you just have a sign flip on this QDHMC, it works out the same way, right? We can basically show that our proposal function is symmetric, and you can see the details in Appendix B. It's not a crazy proof. You can just go through and do this whole derivation basically by just reducing the qualities out. So that's interesting result, but not entirely unexpected in the sense that basically we showed this is very similar to doing HMC. So of course it's a valid sampler in all the regimes of interest. So now we have some numeric experiments, and I think I emphasize this in the paper as well, but these are not at all like trying to say, oh, this is better than HMC, why would we ever do nuts when we could just do quantum HMC? It's more just like understanding and evaluating when things can potentially be interesting. And so, for example, we're looking at low temperature regimes for now, 0.1 and 0.001. Remember, low temperature regimes sharpen the landscape and can often make sampling more difficult. That's why, for instance, like in this whole simulated annealing and other sort of annealing-based methods, you have to start at a high temperature and then decrease over time. And we just plug all the parameters into Tuna, which is just a method for optimizing hyperparameters, just to make a little bit of a fair comparison. We don't want any HMC people coming out and saying, hey, you just did terrible parameters. This is a stupid comparison, I mean, it is like, how valuable is the comparison? TBD, but it is sort of pedagogical in the sense that if we look at the left figure here, figure 2, this is over 10,000 iterations on just some collection of 2 and 3D optimization problems. We can see the convergence. I guess the number doesn't really matter in some sense. I'm not sure, and as a function of iterations. And this is just like the mean energy. So this again isn't like a super impactful metric, right? There's a lot of metrics you could use when sampling. And so what we see here is that in the higher temperature regime, there's not a huge discrepancy between the two samplers. But in the lower temperature regime, we see a larger discrepancy, and that's something we'll explore in a little bit. Is that maybe this quantum situation could be interesting to explore in low temperature regimes where sampling is harder. And the reasoning might be, right, that, and this is just me, making things up. The reason might be that we're not doing anything inherently like quantum in the same way that we are in the same way that the quantum enhanced paper does. I mean, we are doing quantum dynamics, right? We are like definitively simulating quantum dynamics, but we're not like the problem landscape isn't necessarily like guaranteed that like, oh, a Rosenbrock function is just better to do quantum dynamics on. And so but looking at sharper landscapes, I guess, might give us information where having sort of better integrators, which is essentially the idea here, is that we can efficiently simulate quantum dynamics on a quantum computer because that's what quantum computers are good at. And so the idea is that maybe the regimes like that is where this quality of integration might matter. And so that's just, we just plot that on some results. I'm going to skip one figure for now and go down to, figure 4, which shows the acceptance probability for if we pick the temperature to be 0.1 and we plot the acceptance probability as a function of temperature using the same parameters. We see here that we have a much higher acceptance probability in the quantum case when we have low temperature regimes, which once again highlights why we might be interested in this as a regime. Of course, I encourage people to explore more, and this is very much the vibe of this paper, right? Is here's an algorithm that it uses quantum computers to simulate quantum dynamics much better than a classical computer could. Go nuts, see what you can find. And so, we're just trying to hint at things that might be interesting to evaluate. So following up on that, we look at the classic, effective sample size estimation in the top right. This is actually just autocorrelation time effective sample size. It's just like 1 over autocorrelation time. And you'll notice that this is like an estimate as a function of samples. So really realistically, you only really care about the last point. This is just saying like, look, we're converging to an estimate. And the point here is that the lower the autocorrelation time, usually the better things are, because what that means is, right, if you have a sampler and you say, okay, I drew a sample, now I'm going to wait time t, which is really, number of iterations. This basically says how long do you have to wait in order to draw another sample, because if you draw a sample before this, you have it's a biased sample because it's biased on the previous sample. It's like the conditional is non-trivial, and so it's auto-correlated. That's right. Auto is like the self-correlation, and so we want that to be as small as possible, because the smaller it is, the smaller amount of time you have to wait to draw another sample. And so that's why 1 over it, you want a high effective sample size, because you want the bottom part of that to be small. And so basically what we're just showing here for a double well problem is just, hey, look, the affected, or the tau, which is the autocorrelation time, is smaller. And that's just like why this is just sort of saying, why is this sampler potentially better? And that the trivial explanation is, oh, it's better because the effective sample size is larger. And so what we can finally talk about now, first I'll just remark that we do this for all problems that we evaluated down here in figure 6. And you can see, as a matter of fact, that QDHMC is not universally the best if you look at, for example, Gaussians. And I'm a big fan of these figures. I like the little log plots. It's just a very satisfying figure. And so, yeah, you can see it is not universally the better sampler. So, I encourage people to try it out and see when it is or isn't. But the last thing is that where does the speedup come from? Basically, is there a speedup is the first question, I guess. There is a speedup in the sense of, if you were to simulate this on a classical computer, you have to do things very slowly because you're sort of simulating quantum dynamics, and that's painful to do digitally. So in that sense, yes, right? Like if the idea is that quantum dynamics is better at proposing, then it's like absolutely quantum computers unquestionably will be better at this. But then there's the question of like if they're not like if quantum dynamics isn't universally better, then when are the regimes of potential speedups? Now, of course, we already talked about the problem regimes, but the other important consideration is what other people have looked at in terms of regimes of interest for quantum enhanced MCMC. So in the original case, they basically looked at this Ising model problem and were like, the spectral gap looks pretty nice. Let's just do QED MCMC, and it's very robust to noise because it's sort of a random algorithm anyway, so a little bit of noise never hurt anyone. But then some follow-up work showed, in the worst case, most general case, you don't really have any advantage. That's not super surprising. I don't know if the original quantum enhanced MCMC paper actually claimed any sort of universal advantage. But in the worst case, there's no advantage. So then it's like we have to find problems or regimes in which there is actual potential speedups. And so one potential regime for us is in the QDHMC, right? In low temperature regimes, quantum dynamics is basically a Grover search where you just have a sort of narrow Gaussian as a target state. And so that's, Grover, of course, known to have a quadratic speedup. So maybe that's why there's lower temperature regimes are interesting. That being said, even high temperature regimes could be interesting because, right, the quantum dynamics we're simulating operate differently than the classical dynamics you simulate in HMC. And so you can get very non-local updates. And so you can see this in this figure right on the left where you have HMC that goes over to double L, whereas QD-HMC is able to just immediately jump over. Now, to be fair to HMC, I tried to increase the step size. Basically, I tried to tweak the parameters to get it to nice jumps, but it would just explode. If you did that, it's not super surprising. And again, to be fair to QD-HMC, this does not happen all the time. This was, picked to be the best looking one, but there are times when it bounces around a little, then jumps over. But, the point is that HMC would never do this. And so this is a very high temperature update. T is 100, which is like, right, that's 3 to 4 orders of magnitude larger than every other figure before. So there is also interesting, maybe high temperature regimes are also interesting, even if HMC has a high acceptance probability, if it doesn't propose steps that are as good necessarily, even if it accepts all of them, but they're only incrementally better, then it's not really what you want. And so, this is really just saying like, here's a potential interesting algorithm. Go try it out. Show it doesn't work. Show it does work. Show what problems it works on. Show what problems it doesn't work on. I mean, there's been a bunch of follow-up papers to the quantum enhanced MCMC. In fact, I'm going to looking at the papers that cite it. If I go to sort by date, we can see, right, even recently, right, there's work on figuring out on what problems. This is another work. This team actually did a nice paper on showing the limitations of quantum enhanced MCMC. And now this paper is saying like, when are there speedups? Under what regimes is the spectral gap interesting? There's also, this was another one actually just published in, I guess we cite that in PRR, which is the same APS journal we published ours in, talking about, doing quantum enhanced MCMC, but with a different ansatz, a sort of improved and potentially learnable ansatz. And so you got some more nice spectral gap plots here. I will say discrete MCMC is nice because you can just be like, bam, spectral gap, that's all that matters, But you can't construct an exact transition matrix, of course, in the continuous space. So there's a lot of interesting research, I think, going on, and I think this is a very fresh field in the sense that there's room for a lot more research to go on. And so, yeah, as always, you can always, ask questions. I got some emails asking about, specific details of the paper, but in general, I try to be as transparent and open about all these things as possible. And in line with that, there's of course, an implementation available of all of this. In fact, you can, I think for most of the figures here, you can literally just run the code. Like I just uploaded the code that made these figures. Sometimes papers release code and it's like, okay, it's the building blocks, but it's like I have to do a ton of work to recreate the figures and it doesn't always work. Well, if you go to this repository, of course I will link it, and go to this branch. I've made some improvements, and you say like, let's look at the acceptance comparison, right? This is literally just a figure that goes directly in the paper. Or it's like, oh, I want to look at the autocorrelation, right? Shout out to MC, which is just this package here I just took all of their autocorrelation work, and this is just exactly right. This is just the figure that got generated. So, definitely there's a trajectory comparison. You can try it with different problems. You can try it with different, different things. So, yeah, feel free to play around with it. But the key thing is that everything, you want to plot the wave function, you can do that. This is the energy comparison. This one takes a long time to run, just be aware of that. The key thing here is that we're building on CVTFQ, which I talked about earlier in the video, and this is all built on TensorFlow probability and TensorFlow quantum. It's a bit of a interesting implementation. Definitely don't know, if it's super expandable or universally flexible, but basically we make this circuit and then we say, okay, do randomized trauterization each time, take one sample, and then sort of do the whole process. And then we have an HMC wrapper here that just does the chain sampling depending on how you want to do it. So this is the basic idea, right? We're just building on CVTFQ to define a circuit, and then we parameterize the circuit with random values, and then we just give a singular sample here. And so this shows the self.sample, which I don't think I usually use in my TFQ videos. So that's all the code as well. I think let's just look at all of these. I think that's everything to be discussed in this video. So as always, I will try to remember to link everything in the description, and I will see you all next time.